In the previous video, I showed you how to use Hess's law to calculate the heat change for a reaction. Hess's law says that the heat of reaction is the same whether we think of the reaction occurring in one step or in a series of steps. This works because enthalpy is a state function. It depends not on the pathway in which the reaction occurs, but only on the initial and the final conditions. What we did in the previous video was take thermochemical equations, manipulate them so that they algebraically added together to produce the reaction in question. When that occurred, we could add the delta H values together to calculate the heat of reaction for the reaction in question. A second method for calculating the enthalpy change for a reaction is to use heat of formation values. These are delta H values themselves, but heat of formation refers to a very specific reaction. Heat of formation refers to the change in enthalpy when 1 mole of a substance forms from its elements in their standard states at 25 degrees Celsius. By this definition, 1 mole of hydrogen gas plus half a mole of oxygen gas producing 1 mole of liquid water represents the heat of formation reaction for H2O. This reaction does not represent the heat of formation for water. Why not? Because it produces 2 moles of water. Part of the heat of formation definition is that 1 mole of the compound is formed. Additionally, this is not a heat of formation reaction because it's not forming the compound from its component elements. It's forming one compound from other compounds. It's really important that you understand this definition of heat of formation, that you understand the specific reaction that heat of formation goes with. If you still need some help understanding this, look at this page on the Chem Team website. You can look up heat of formation values for many compounds in Appendix 2B of your textbook. Also, the delta HF value for a free element in its standard state is 0. Think about it. Heat of formation is forming the substance from its elements in their standard states. Free elements in their standard states don't form from anything else. That is their natural state. So they have no heat of formation value. To calculate delta H for any reaction, take the sum of all the heats of formations of all the products and subtract the sum of all the heats of formation of the reactants. Look at this reaction. Here, we need the heat of formation of 2 moles of Fe2O3, and we need to subtract from that the heat of formation of 4 moles of FeO. Why am I ignoring the O2? Because it's an element in its standard state, so its heat of formation value is 0. So to calculate delta H for the reaction, we look up the heat of formation of Fe2O3 in the textbook. You find that the value is negative 826 kilojoules per mole. Since there are 2 moles of iron 3 oxide in this reaction, we multiply this heat of formation value times 2. That's our only product, so that is the sum of all our products. We're going to subtract from that the sum of all our reactants. We look up the heat of formation of iron 2 oxide and find that it's negative 272 kilojoules. Multiply that by the 4 moles present in the reaction. And again, we don't have to include the O2 because it has a value of 0. The final answer is negative 564 kilojoules. Look up the delta H values in the back of your book and complete this question. The delta HF value for SO2 is negative 297 kilojoules per mole times 2 moles in the reaction. We can write that we add 0 for oxygen just to remind us. We subtract from that the sum of all the reactants, which is negative 396 kilojoules per mole for SO3 times 2 moles present in the reaction. The answer this time is 198 kilojoules. The third and final way we will use to calculate heats of reactions is using bond dissociation energies. This is the energy required to break a bond. So first, you need to understand that energy has to be put in to break a chemical bond, and energy is released when a bond forms. Energy put into a process is a positive delta H. When a process releases energy, that's a negative delta H. So in chemical reactions, the bonds in the reactants are broken. That requires energy input, positive delta H, and new bonds of the products are formed. That's energy released, so that's a negative delta H. So to calculate the heat of reaction using bond energies, you sum the energies of all the reactants' bonds and subtract the sum of the energies of all the products' bonds. Notice that reactants and products are switched compared to when we were using delta HF values. And it's because of this sign convention. Reactant bonds are broken, requiring energy, which is a positive change. Product bonds are formed, which releases energy, which is a negative change. Bond energy values that you look up in your book are all positive, so they represent the energy to break that bond. We need those numbers to be negative when the bond is forming on the product side, so we subtract all the product numbers. Subtracting makes all the values negative for us. For now, all compounds will be drawn out entirely for you. Once we've done our unit on bonding, though, you'll have to draw these for yourself. You have two options on how to solve these. You can account for every one of the bonds shown. You can break all the reactant bonds and form all the product bonds. Or you can look for bonds that reform exactly the same as before and leave those out of the calculation. For example, here you have an H to C to H set of bonds that reforms in exactly the same way on the product side. Mathematically, if you put those numbers in on the reactant side, you're going to then subtract them out because they're on the product side. So those numbers would cancel themselves out of the math. Same thing happens here with an H to C to H bond. You can ignore those because they reform in the same way on the product side. So all we really have to account for is this carbon-carbon double bond, this hydrogen-hydrogen bond. We're forming a carbon-carbon single bond, and we're forming a C to H bond in two places. One thing to note here, this double bond, a double bond is a unique type of bond. It's not two single bonds together, so you can't do this math by breaking one of the two bonds between the carbons. It's not like that. You have to fully break the double bond and form the single bond. So to calculate delta H for using bond energies, we're going to do reactant numbers minus product numbers. The bond energy for a carbon-carbon double bond is 614 kilojoules. We add to that the bond energy of the hydrogen-hydrogen bond, which is 432. That's all our reactant numbers. We subtract from that the numbers for our products. A carbon-carbon single bond has a bond energy of 347 kilojoules. And a carbon to hydrogen bond is 413 kilojoules. We need to multiply that by 2 because there's 2 of those bonds forming on the product side. Adding up these numbers, we get that the heat of reaction is negative 127 kilojoules. There are 3 different ways that we just saw to calculate the heat of reaction. We can use Hess's law when we have existing thermochemical equations to manipulate and to add together. We can use heat of formation values, and we can use bond dissociation energies. The method used depends entirely on which type of information is provided in the question.